Hello all, welcome to the Chemistry EduHub channel. I'm going to create chemistry videos from grade 8 to 12 of State Board and CBSE and IIT syllabus and NEET, which is useful for all competitive exams. So do check out the remaining videos in my channel and follow for more updates. And in today's video, let us start reaction intermediates. So we are now dealing with the organic chemistry basics. So in which we talk about reaction intermediates. So generally most of the organic reactions are multi-step reactions. If you see in case of inorganic chemistry, the reaction happens in a single step. Reactants convert into products, that's it. But in case of organic chemistry, the reaction takes place in more than one step. So they are complex reactions. So in such case, in any of the steps, we get intermediates. Now what are these intermediates? Which have a very short span of life, and they convert into the products. So reactant convert into some intermediate and then it converts into products. So such substances are called intermediates. We have many intermediates in the organic chemistry like carbocation, carbanion, carbon free radical, carbenes, benzene, etc. So we are going to deal with each and every intermediate clearly and how it is formed, what is its structure, how it is stabilized, everything. The first intermediate is carbocation. So carbon containing species could be a methyl or tri-substituted, disubstituted, ethyl, any carbon compound which contains positive charge is considered to be carbocation. This is a methyl carbocation. If at all around the carbon there are 3 R groups, then its arrangement is going to be somewhat this way. So carbon with 3 R groups and positive charge is said to be a carbocation. So this is the most common intermediate that we see in many of the reactions. Now since there is positive charge on the carbon, carbon's valency is generally 4, but here it is only 3. That means there are, instead of 8 electrons, there are only 6 electrons. So we consider it as electron deficient species, or since it is electron deficient, it will be always ready to take up electrons. So it is considered as electrophile, which means electron loving or electron liking. So carbocation is an electron deficient species and electrophile. So generally carbocation has no lone pair of electron. Of course, as it is electron deficient, it has no lone pair on it. And we see the carbon is surrounded by 3 bonds with no lone pair. So whenever carbon has only 3 bonds, its hybridization is going to be sp2 hybridization. When there is sp2 hybridization for carbocation, its structure is going to be planar and the bond angle is going to be 120 degrees. And the arrangement will be generally this way. And the orbital with electrons with positive charge. So this is the general representation or orbital picture for a carbocation. There is a vacant p orbital. Since it is sp2, carbon has 4 valence electrons, 4 orbitals in the valence shell. So only 3 are used. Remaining 1 p orbital is unhybridized and it is vacant. It is not involving in hybridization and it is vacant. So this is the structure of carbocation and its description. Now let us see what are the reactions in which carbocation can be formed. Now let us see 1 or 2 examples where the carbocation can be formed in the reaction. So first is the solvolysis of CX bond. Solvolysis is nothing but by using a solvent we break the bond between carbon and hydrogen. So whenever carbon cannot be directly taken as carbon, we take R group. So our X bond is broken by using some solvent it need not be always water, it could be any organic solvent. So when this is broken, we get R plus and X minus. This bond is broken and we get R plus and X minus, because generally X is electronegative and R is electropositive. So definitely X gets the negative charge and R gets the positive charge. Now this is considered to be your carbocation. This is one general example where we could see the generation of carbocation. And if we look at the protonation of alcohol means addition of proton to alcohol. So we take ROH as alcohol, then we add H plus. So what is H plus? Electron deficient species. Obviously OH has 2 lone pairs. What it will do? It will donate lone pair to the H plus. So obviously we are going to get OH2 plus. Now this is unstable, so it results in the formation of R plus plus H2O. Now this is your carbocation. This way carbocations are generated. Now this carbocation will not stay for a long time. This is going to combine with some other nucleophile and turn into the product. So these are the few examples where we can see the carbocation formation. Now let us see what factors are going to stabilize the carbocation. First is the less electronegativity of carbon. Now what is this? Suppose if the electronegativity on the carbon is less, for example there is methyl attached to CH2. Now this is said to be more stable compared to the vinyl carbocation. This is said to be more stable compared to triple bond containing carbocation, because as the double and triple bonds are formed, the electronegativity is going to increase, acidic behavior is going to increase. So that means simply the carbon has to be sp hybridization instead of sp3 hybridization instead of sp2 and sp. Then the electronegativity of the carbon is going to be less and the carbocation will become stable. And the second factor is the plus I effect. Plus I effect is nothing but electron releasing group present on the carbon. So whenever there is electron releasing group, that will stabilize the carbocation by donating electrons. So obviously methyl carbocation is less stable compared to primary, compared to secondary and compared to tertiary carbocation, because of the more number of plus I groups on methyl, then then secondary and tertiary carbocations. Similarly, hyperconjugation and resonance. Hyperconjugation and resonance are going to support the carbocation stability. So if you look at resonance example, so adjacent to the carbocation, if there is a pi bond, then this will result in the compensation of the positive charge of the carbocation and it becomes more stable compared to the carbocation with no pi electrons in the adjacent carbon. So this way resonance and hyperconjugation are going to help the carbocation stability. So this is the complete information about carbocations. The second intermediate is carbanion. This is nothing but the carbon with negative charge. So the same way as exactly opposite features we are going to see in the case of carbanions to that of the carbocations. So carbanion is formed by the removal of one atom or group from the carbon. Suppose if there are 4 groups like this around the carbon, if one group or atom is removed without removing the bonds, then what happens? This is gone as H plus and the bonded electrons will shift onto the carbon. Now this results in the formation of what? Carbanion, carbon with negative charge. So carbanion is having 3 bonded pair of electrons and 1 lone pair, or you can say unshared pair of electrons. These are 3 paired electrons and 1 is unpaired electron. So accordingly it will show sp3 hybridization. Carbanion is sp3 hybridized and it is surrounded by how many electrons? 8 electrons. So it is not electron deficient. So generally this carbanion is going to be arranged in the form of pyramidal shape instead of tetrahedral. Whenever there is sp3 it has to be tetrahedral, but here it is pyramidal geometry. It's because carbon and hydrogen's electronegativity is not very different, the difference is not very high. In such case the repulsions are not going to be that high. Because of that the arrangement is pyramidal instead of tetrahedral. Okay, this is about the carbanion and its structure and arrangement, orbital structure also. Now let us see what are the factors that are going to stabilize the carbanion. Exactly reverse of that of the carbocation, we observe the factors. What are those? One is more electronegativity of carbanion, carbon. The other is minus I effect, that is electron withdrawing groups should be present on the carbon. Then earlier we said hyperconjugation, but now here it is reverse hyperconjugation. So if you have doubt about what is reverse hyperconjugation, there is a video on reverse hyperconjugation, you can go check that out. So reverse hyperconjugation supports the carbanion stability. Then comes the minus R effect. Since carbanion is electron rich, all the factors or all the phenomenon where the electron withdrawing is present, that will support the carbanion stability. So accordingly we can see if it is ethylene, if it is ethyl, it will have least stability. Then if it is ethinyl, then it will have more stability compared to ethinyl carbanion. So exactly reverse to that of the carbocation we observe. So ethyl carbanion is less stable than ethinyl than ethinyl carbanion. So, and if you consider the simple carbanions also, here the order is reverse. Methyl carbanion is more stable than primary, than secondary, than tertiary. So this is the stability order and the factors that stabilize the carbanion in the reactions. The third intermediate is free radicals. Free radicals are nothing but the carbon species or any species which have odd electron on them. Now here we are dealing with organic chemistry, so we consider only the carbon free radicals. Now how a free radical is formed? Whenever there is a bond between two atoms, bond indicates 2 electrons. When these 2 electrons are equally distributed, I put a different arrow here instead of complete arrow. It is a half-headed arrow. We call it as fish hook arrow. We use it only when the free radicals are formed. Okay, so that means the bond that has 2 electrons is equally distributed among the 2 atoms. That results in the formation of free radicals with odd electrons. Okay, so now this free radical can be either planar with sp2 hybridization. The possibilities are 2. Either it could be planar with sp2 hybridization, or it could be neither planar nor tetrahedral. Neither planar nor tetrahedral, and exist in the form of equilibrium form as a hybrid between p and sp3. I will show the orbital structure also. So planar form is going to be this way with R, R dash dash, three different, this R dash dash dash, this indicates different alkyl groups, and there's an orbital with odd electrons. Okay, this is the planar form of an free radical, or it could be neither planar nor tetrahedral. Indicates what? It is either pyramidal this way, or this way. It always stays in the dynamic equilibrium, which moves continuously from one form to the other. So free radicals are expected to be either in the planar form or in this form, but we cannot say exactly which form is certainly exist in the reaction intermediate, but mostly we expect the free radical to be in the planar form only, in the sp2 form, where we see the odd electron in the sp2 hybridized carbon and also an odd electron in the p orbital. So this gives you the slightly pyramid shape, or we can say planar shape. This is the free radical orbital structure, and generally we observe free radical formation in the photochemical or thermal reactions, where the amount of energy that we supply is going to be very high. In such case, we observe the equal sharing of electrons, that is called as homolysis. Equal breakage of the bond between the two atoms that results in the formation of odd electron species. This is considered to be the formation of the structure and the orbital formation of free radical. Let us see one example. You can consider methane with chlorine. So generally the free radical formation takes place in three different steps: chain initiation, propagation and termination, where you can see the formation of methyl radical and chlorine radical, and then methyl radical again combines with chlorine, chlorine radical again combines with methane. Likewise the chain propagates, and ultimately methyl radical and chlorine radical combines to give methyl chloride. Likewise the reaction continues. So such homolytic reactions will generate the free radicals. Now what are the factors that will support the free radical or stabilize the free radicals in the organic reaction? Is the first thing is hyperconjugation. First phenomenon is hyperconjugation, and the second phenomenon is resonance. Now these two are going to be supporting the stability of supporting the stability of free radicals. So if you look at methyl free radical, this is less stable compared to ethyl, less stable compared to secondary, less stable compared to tertiary. Now here we have 3 alpha carbons with 9 hydrogens, 2 alpha carbons with 6 hydrogens, 1 alpha carbon with 3 hydrogens, and no alpha carbon with 0 hydrogens. So this way hyperconjugation is supporting the stability of free radical. Similarly, resonance is going to stabilize the allyl and benzyl free radicals. What is an allyl free radical? Whenever there is a double bond, ethylene, one of the hydrogens, if it is replaced with methyl, now this is considered to be allyl. Double bond attached to some group, such arrangement is called allyl. Now this is stabilized by the resonance, because this will shift here and you can see the free radical moving from this carbon to this carbon. So this way resonance will stabilize the allyl free radicals. Similarly, benzyl group is nothing but benzene with CH2 instead of CH3 with a free radical. Now this is considered to be benzyl free radical. So we observe this pi electron moving this way. So accordingly, this again shifts here, this again shifts here. Likewise, you see the resonance stabilizing the benzyl free radical. So this is about complete information about the free radicals. The next or the fourth intermediate is nothing but carbene. Carbenes are considered to be neutral. That means they have no charge. They are neutral with no charge, and they are divalent. That means they are bonded to two other groups at a time, and in which these carbenes are those in which we see the carbon is bonded to two atoms, let's say RR or RR dash, and has two non-bonding orbitals that contain two electrons in them. Now this carbene can have two different kind of arrangements, and we call them either singlet or triplet. So when do we call them singlet and when do we call them triplet? So suppose the arrangement is same, this is considered to be a singlet, whereas instead of paired electrons, if there are two electrons with the same spin, in case of singlet, the paired electrons are having opposite spin. In case of triplet, the paired electrons are the electrons are not paired, and both are with the same spin. Such kind of arrangement is said to be singlet and triplet. So carbenes are expected to be in either singlet form or in the doublet form. Now if you look at the structural arrangement of singlet and triplet carbene, singlet carbene is having sp2 hybridization, where out of 3 hybrid orbitals, 2 are utilized by the bonding atoms, 1 is utilized by the shared pair of electron, that is unshared, like the lone pair of electron, and this is the unhybridized p orbital that is left vacant. And now this is going to be very close to the structure of that of the carbocation, whereas the triplet form, if we consider, the triplet form is sp hybridized. The triplet form is sp hybridized, and it is either linear or non-nearly linear species. It is linear or nearly linear species. Now these are the two types of carbenes: singlet with a pair of electrons, triplet with parallel spins, or the two electrons are having the same spin. We call them parallel spin. These are the two forms. And if we consider the energy of singlet and triplet carbenes, initially we consider that whichever has paired electrons, that will have the lesser energy, but according to the studies, triplet form is having lower energy compared to that of the singlet form. It is because to overcome the repulsions between the electrons and to get paired, the energy required is higher. So singlet form is of higher energy and triplet form is of lower energy. So this is the basic information about carbenes, and their stability is generally supported by the resonance. Resonance will stabilize the stability of the will support the stability of the carbenes. If we look at the decreasing order of the stability of different singlets, it is CF2 greater than CCl2 greater than. We are looking this order only in the singlets with different halogens. These are the different singlets. So fluorine has more stability compared to chlorine, compared to bromine. So the most common reason that we can give is the electronegativity. So fluorine being more electronegative, it's more stable compared to chlorine and bromine. So this is the information about carbene. The fifth and the last intermediate is benzene. So benzene comes under the category called arynes. Benzenes are generally categorized under arynes. Now what is an aryne? Aryne is an aromatic compound. Aryne is an aromatic compound that has a triple bond. So we have already seen what is an aromatic compound. It should be cyclic with pi electrons. So in the cyclic ring with pi electrons, generally we observe only double bonds. But here in case of benzene, there is a triple bond. Such compounds are considered to be arynes, and the best example for aryne is benzene. Okay, so it's generally like inside the ring we have an acetylene, it's like that. Or if we look at a benzene ring and there is one hydrogen here, suppose if we remove these two hydrogens, what are we going to get? We get a triple bond over here. Such similar structure is of benzene. So what is the other name for benzene? It is dihydrobenzene. When you remove two hydrogens from benzene, we can expect the formation of benzene. So what are all the names that benzene has? Benzene comes under the class arynes. It is also called dihydrobenzene. Now the triple bond in the benzene, it is not formed simply by the overlapping of unhybridized p orbitals, just we observe in the case of acetylene. It's not like that, because it's not possible in the case of aromatic compounds. It is formed by the overlapping of the orbitals of neighboring carbon atoms. If we look at the benzene structure, so here the carbon has p orbital, here also the carbon has p orbital, then we observe the overlapping this way. Now this results in the formation of the third bond, that is the triple bond. Okay, so such arrangement leads to orthogonal form inside the benzene ring. This way a triple bond is generated in the benzene, unlike in the case of acetylene where the sp hybridization is possible. Okay, let us see a few examples where the benzene is generated. So whenever there is benzene ring with fluorine, bromine, or fluorine, bromine, when we add magnesium or lithium, then we observe the formation of, if we take lithium, then we expect the formation of lithium, bromine replaces the lithium replaces the bromine, then we expect the benzene formation this way. Or if we use magnesium instead of lithium, fluorine, bromine, if we add magnesium to this, magnesium, lithium, these are all the strong bases. Only in the presence of strong bases we can expect the benzene formation. So we get benzene and the byproduct is MgBrF. So these are the few examples where we observe the formation of benzene. So this is the complete information about reaction intermediates in the organic chemistry. So if you find this video helpful, please like, share and subscribe. Thank you.